All right, hello everyone. Welcome to one more day of the Lisbon Machine Learning School. It's a great pleasure to have with us today Ivan Titov. Ivan is an associate professor at the University of Edinburgh. He's also a part-time faculty at the University of Amsterdam. Before that, he was a junior faculty professor at Saarland and a postdoc at the University of Illinois at Urbana-Champaign. He received his PhD in computer science from the University of Geneva in 2008. And Ivan's research interests are in natural language processing, which includes both semantics and syntax, and machine learning, including structure prediction methods, latent variable models, and Bayesian methods. His research is supported by personal grants, which includes a ERC grant, and several industry funding and various collaborations. Thanks a lot, Ivan. So we are going to play your recorded video and then have some QA.
Hi everyone, and welcome to my talk on graph neural networks in natural language processing. My name is Ivan Titov, and this talk will include discussion of joint work with my colleagues at the University of Edinburgh and the University of Amsterdam, and especially Nicola De Cao, Diego Marchiani, Yasmine Bastings, Michael Schrickel, and Wilke Aziz. I suspect all of you are familiar with the state of affairs in NLP in 2020. So carefully designed models for individual NLP problems with carefully crafted features, carefully crafted conditional independence assumptions have largely been replaced with very flexible, generally task agnostic, very large and very effective narrow models. And as an illustration of this type of models, we have a picture of encoder-decoder frameworks. And encoder-decoders will show up in a few places in this talk, so it makes sense for us to recall what they are. So encoder-decoders consist of two components. One is the encoder, which reads the input, in this case, a sequence of words, a sentence in English, and produces a representation of this sentence, which is passed to another component, to the decoder, which generates a prediction. So in this case, it generates a translation of this sentence, generates it word by word. So these models have been hugely successful. We've made advances on many different problems, and maybe even managed to approach some of the problems we hadn't solved is possible in a short term. Still, these models are of course not perfect, so there are many hard problems on which we still need to improve a lot. And also these models have such drawbacks as the lack of interpretability. So you can hope that we can address these problems by injecting in these models prior knowledge about the world, so facts about the worlds, and also prior knowledge about the language, how it's structured. So natural question to ask is, how do we represent this prior knowledge? So we can think of graphs as potentially the most natural representation of prior knowledge. And these graphs can represent facts as knowledge bases, knowledge graphs, and you have a tiny little example of a knowledge graph in the bottom right corner of the slide. And you can also think of syntactic or semantic representations of sentences, and you have a syntactic dependency tree and also shallow semantic dependency graph for this short sentence at the top of the slide. But you can also think of representation of larger units of the whole documents, or maybe even collection of documents. For example, coreference chains, graphs which link mentions across documents and within documents, mentions of the same entities. Or you can also think about discourse relations which relate fragments of text. So now, how do we represent how do we encode, how do we incorporate this type of graphs in modern NLP problems. And this is where graph neural networks come into place. So this outline of my talk, I'll start by discussing graph neural networks and what they are and what kind of limitations and what kind of power they have. And then we'll discuss how we can incorporate graphs into narrow encoders using GNNs. And then we'll look in slightly different setting where we use GNNs to perform reasoning in knowledge bases and then link these two things together. Towards the end, we'll touch on topics which I refer as advanced topics, but basically some ongoing work which is interesting for me, for my group, and hopefully interesting for you. So graph neural networks. You can think of graph neural networks as a generalization of convolutional neural networks. So you have a graph convolution instead of convolution on the regular grid. So convolution you saw perhaps in the image processing in computer vision context operated on a regular grid. For example, 2D grid, as you can see on the left. Graph convolution relies not on the neighborhood on the grid, but on the neighborhood defined by the graph. And this is kind of hand-wavy high-level connection between the two, which is maybe gives you some intuition about graph neural networks. For certain type of graph neural networks, this connection can be made more formally, but I'm not going to talk about this in this talk. We will use terms in the talk graph convolutional neural networks, GCNs, and graph neural networks, GNNs, interchangeably, as seems to be common now both in NLP and machine learning. So what do graph neural networks do? So what essentially happens, they start with some initial representation of nodes, which can be just node IDs or some kind of features of these nodes, and produce new representations of these nodes by propagating information along the edges. So let's just have a look into individual single update in the graph neural network, and also perhaps in the simplest form of this update. So let's look into node V, the red node, in this little graph. So what happens, it receives messages from its neighbors and also from itself. And in the simplest case, these messages are just linear transformations of the node representations. So the linear transformation is parameterized by this matrix W. And then these representations are summed together and pass through some form of nonlinearity, which is in this case is ReLU, so rectified linear units. And you obtain a new representation of these nodes. The power of graph neural networks comes from the fact that these updates are applied to all the nodes in a graph in parallel. And also you have multiple layers of message passing of graph convolution on top of each other. So again, we start with some initial representation of the nodes, features, IDs. Then you obtain a representation after one hop, one step of message passing, and this representation is informed only by individual immediate neighbors of the nodes. Then you get a representation in the second layer, so information about nodes 2 hops away gets integrated and so on. And in the end, you obtain some representation of the node, which you can use to make some predictions. So these representations, these predictions can be used in different types of predictions. So you can think of predictions for individual nodes, for example, node classification. So in that case, you will have tiny little classifier on top of every node. For example, feed-forward neural network with softmax on top. And then if you have labeled data, you will train this model, so parameters of both graph neural network and the classifier in an end-to-end fashion to predict the labels. Or you might have also classification of the entire graph. Then you need to integrate a pool information from the entire graph, aggregate this information. So you can do, for example, mean pooling, and in this case, you just average representation of all the nodes and make a prediction, or it can be max pooling, or it can be something smarter than that. So that would be graph classification. So now we got a bit of a sense what graph neural networks are and how they look like. Let's think how we could apply this in NLP context. In NLP, we typically have labeled and directed graphs. So the labels can be, for example, syntactic relations. And there is a straightforward, of course, way to integrate this label and direction information in Genon update. So this would be to say that every matrix is specific to the edge label and also to the direction. And this is one of the versions of what is known as relational GCN and also syntactic GCN. Of course, this choice of parameterization is rather important. For example, you wouldn't want to do this if you have very many relations. So there are different ways how you can parameterize the model. So one example, for example, what you could do, you could integrate a gate, and this will be just a multiplicative factor for every edge. And this gate is again predicted from the edge origin representation with a linear function. And in this way, it can decide if this message should be disregarded or maybe downweighted or should be kept unaffected. So this may be something which is useful often in NLP. For example, you can imagine that only parts of syntactic graph may be relevant to certain prediction task, and you should just provide inductive bias that it's easy to learn to drop certain types of edges. And this was what's happening in syntactic GCN. But this is just one example to give you some idea of the space of what you can do, would have been done in a previous work. But more generally, you can see of almost every GNN as a message passing GNN, which consists of application of two functions. So one computes a message and one decides how do you aggregate messages. So message function generally would be some parameterized function of edge origin, so representation of the node at the origin of the edge, and the representation of the node at the destination of the edge, and also direction of a label of this edge. So now you obtain a vector, a message, and you need to aggregate them. So what you would do is typically sum these messages together and use some another function to which I refer here as aggregation function. So summation is rather important because graphs are invariant to the reordering of its neighbors. It's at least the neighbors of the same type encoded by the label. And so graph neural network should be also invariant to this permutation, and summation guarantees this. So if you're interested in the different permutations and how well they work on the different tasks, I highly recommend you to have a look in a recent paper by Brockschmidt, where he looks into GNNs for labeled graph, and appeared at this year ICML. One question is you can ask is how expressive GNNs are. And roughly speaking, GNNs can compute any function which is a Turing machine can compute, as long as aggregation and message functions are sufficiently expressive, and also nodes are distinguishable from each other. So, for example, they have different IDs or unique features. And we'll touch on this property and why this is important in a moment, because I think it has certain practical implications. But for this result of Turing universality, you can ask, why do we care? And in principle, we always applied GNNs. We learned them with stochastic gradient descent. We learned them from a finite size data set. So why do we care? Why this is practically relevant? I think what is potentially more practically relevant is not what is learnable, but is what is not learnable is a given architecture. because often in NLP, we might have certain intuitions about features, right? We have been designing, many of us have been designing these features for years, and understanding if these type of features are representable or not is an important thing, I think. So one striking difference is in the representational power of graph neural network with nodes which can distinguish each other and nodes which cannot. And this will be somewhat related to some discussion we will have in the later parts of the talks, because there are certain settings where you might prefer not to have this anonymity. So you need to understand implications of making this decision. So to understand, to give an intuition for what's going on, let's have a look at this very simple example. So we will be trying to understand what a red node knows about the topology of the graph after one update and after two updates, after one hop and after two hops. And first, under the condition of non-anonymity, so all the nodes are distinguishable from each other, so all the nodes have a different color. So after one hop, this red node basically knows that it has neighbors as neighbors blue, orange, and green nodes, and can store this information if it has enough capacity. After two updates, it may receive this type of messages. So messages basically are tiny little subgraphs, graphlets, and there is only one way how you can connect these graphlets together. So after two updates, after two hops, the red node knows the entire topology of the graph, or at least of its connected component. The situation changes dramatically when we have non-anonymity. So for the moment, we assume that nodes are non-distinguishable at all from each other. So after one hop, red node knows only its degree, as long as aggregation function lets it have this information. After two hops, there is still uncertainty about topology, because the degrees sent by the neighboring nodes, these little graphlets, they don't have colors anymore, and they can be connected in different ways together. And this is a fundamental problem. So these models then can't represent sort of features, because the graphs look the same to this node. It can't really represent any features which distinguish these two graphs. So that was about anonymity and thinking about representation, whether you want to break this anonymity and maybe to which degree. But also you can think about the size of the networks and the depth of the networks. And there is a very nice recent paper by Lucas, which looks into what kind of graph problems can be represented by a graph neural network of certain size, so of certain depths and a certain width, or the size of node embeddings. And these are graph problems such as shortest path or minimum spanning tree. And you might say, why do we care about graph problems? But I think, again, in many NLP problems, we may have certain type of intuition what kind of combinatorial, what kind of graph problems need to be solved or approximated to have strong predictive features. And these results may well be relevant to decisions about the architecture of GNNs. Okay, this essentially concludes the first part of my talk. So we defined what GNNs are and looked a little bit into different choices we can make. We also discussed some weaknesses and some pointers to this new, very recent work on about expressivity of GNNs. So now let's look into how we can use GNNs to incorporate prior information into encoders. So basically into parts of encoder-decoder models. Recall, we already saw syntactic GNNs. So syntactic GNNs have been used to encode syntactic structure, syntactic dependency structure, and syntactic dependencies encode bilexical relations between words, syntactic relations. For example, Sherpa is a subject of a predicate climbed, and this is what this arrow represents. So climbed is a syntactic head, and Sherpa is syntactic dependent. And we had an update rules for GNNs, which and the GNNs passes information both along the edges of syntactic tree and also in opposite direction, and also it has self loops. But now, how does it live? How do we plug in this in a encoder decoder? Actually, is in a rather straightforward way. At least the simplest way of doing this is rather straightforward. So what you do, you start with your favorite encoder, which can be transformer, usually will be transformers these days, I think, or some form of RNN, for example, LSTM. This can also be pre-trained encoder, so you're perhaps familiar with models of like BERT, ELMO, RABERTE, and etc. So you obtain a representation of words or tokens, input tokens, and then what you want to incorporate syntactic bias into the model. So you have a syntactic tree produced by a parser. So what you do, you produce in a first layer representation using the first hop of graph neural networks. So yeah, you propagate, you use self loop, so you get, you encode information about the same word in a layer below. You have a propagation, in this case, from dependent to head, so in the opposite direction from the dependency arcs, propagation from head to dependent, so long dependency arc, and you get a representation informed by the immediate neighborhood in the dependency graph. And then you can have a few layers of GNNs which incorporate information, longer passes, effectively longest fragments of dependency structure. So now you obtained at the top layer syntactically informed representations of words, or maybe parts of words, as will often happen if you rely on contextualized embeddings. So what you do then, what you can do then, is to pass not the original representations of words from RNN and transformer, but now the syntactically informed representation to the decoder. So you basically plugged in this GNN encoder in between your original encoder and the decoder. So there are different ways, maybe somewhat more complicated ways, how to interconnect these two, but this is one of the basic ways which has been used with certain success in a number of papers, including our own work. So these are results which are somewhat, maybe even quite outdated. The field moves really fast these days. So these experiments were running in 2016 for machine translation. And what we were integrating here is a syntactic dependency graph, but also a shallow semantic dependency graph, which encodes semantic dependencies. For this specific sentence, they really look alike, but it's not always the case. And what we actually observed is that in terms of blow performance, so the standard metric used in machine translation, we obtained larger improvements by using semantic structure than syntactic structure, and both of them were complementary. So that's also a nice point about GCNs, that you can combine different graphs together. Perhaps even more interestingly, especially now when we have very strong encoders which are super strong on a sentence level, but maybe less strong on a document level, especially cross-document level, is how do we incorporate, how do we apply GCNs on a document or cross-document level? And this one illustration. So this is a multi-hop question answering, specifically data set called WikiHop. In this task, you are given a set of documents question pairs. So this tiny example kind of symbolizes what you have. So you have, in this case, 2 little documents. And then you have a query question, which is really not a natural language, but it's a relation and an argument. So in that case, you need to figure out in which country an entity tourist plan is located. And there are several candidates for the answer. So it's multiple choice QA, and the dataset is created in such a way as to encourage model to do this multi-hop reasoning. So actually aggregate information across multiple documents rather than doing prediction on the using a single document. The way we approached this task is we defined a graph and perform graph neural networks. That's the reason, of course, why I'm talking about this work in this talk. So nodes in these graphs are mentions, and edges connect these mentions, and there are several types of edges, and it's a rather simple set of edges, I would say. So first connects any 2 mentions within a single document, so same document edge type. Then there are also exact matches which connect entities, the mentions which exactly match both across documents, but also within documents. I think my slide just doesn't mention within, but it should be across and within. And also coreferences. So it's basically harder case of these matches, right? So in this case, predictions are made by a coreference system, which tells us these 2 mentions refer actually to the same entity. Plus, on top of this, we have a complement edge. So if 2 mentions are not connected by any edge, then we have a complement edge. So in the end, we essentially have a full graph. Initial node representations are produced from word embeddings, from contextualized ones, or like GLAV. Back then, GLAV was still Elmo. Sorry, contextualized Elmo. Back then, Elmo was still popular, and also GLAV. And we applied a gated version of Genon similar to the one we discussed in the context of syntactic models. So these are results which were state of the art back then when the paper was published. So the best model we had was a lot faster than machine reading models such as BDAF or FastQA, which includes multiple layers of re-encoding with some recursive models. Another advantage of using GCNs, at least in this setup, is that we were able to compute ensembles very cheaply, because overhead of this computation was very small. So this is results are outdated. I think the best models on this benchmark reach performance way higher than 80. But most recent models, I believe, are built using the same type of principles. For example, I think the state-of-the-art model on this dataset is PathGCN, which is improves and has a better graph neural network model effectively. We talked about using graph neural networks in text encoders, so encoding structure of text given as an input to the encoder. But also GNNs have been very popular in the context of encoding structured data. So the input itself wasn't the text, but the structure, but generation, the output, the prediction was the text. So for example, you can consider generation of natural language sentences from logical forms or SQL queries, and there's been a lot of work in that direction. So another interesting application is generation of captions, but not directly from images, but rather through scene graphs. And the scene graphs represent the scene, the semantics of an image, and then encoded using graph neural networks. Another application, which is, I think, is rather cool, is summarization, but not summarization of documents in natural language, but rather summarization of source code, programming code, and also generation of commentaries. Again, graphs are a natural way to represent programming code, so GNNs are a useful tool here as well. So this concludes the second part of my talk. So far we talked about ways to use graphs and graph neural networks to represent prior knowledge about text structure. So we have lots of tools. We've been working for many years on creating structure prediction models, parsers. So why not to use their output? And in many cases, we can get away with even using a simple heuristic, as you saw an example with multi-hop QA. And GNNs are easy and natural tool to use in this setting. And when I talk about easy, this not only means conceptually easy, but also there are lots of tools nowadays which can help you to implement GNNs. And many state-of-the-art models are implemented. So very useful example is PyTorch geometric. I talked often about models which are not so recent in terms of GNNs from 2018, 19, but there is a recent generation of models which are a bit more effective on the benchmark, and they borrow some ideas from other narrow models such as transformer or CNNs. But I would say the key ingredients remain the same. So I think it's a good time for us to have some discussion in a chat. So I'm looking forward to your questions.
Okay, we have some questions in the Q&A. So Ziwon Zhang is asking about the input graphs, our graphs for each sentence in a corpus defines or produced.
I think this question appeared maybe before I talked about GNN encoders, so it might have been answered, but basically we have been working on structured prediction tools, right? And we have parsers, we have coreference systems, and this is one way to produce an input graph. There may be even ways to heuristically define these graphs, as we saw, for example, linking all mentions of entity within document, across document. So this way, basically, inductive bias comes into. So what you would think would be appropriate input representation. And in a few minutes, we will see an example where the graph is knowledge based. That's another type of a graph we can use. Mm-hmm.
All right, another question that popped up by Katya Saveleva. Can anonymity in some way be useful for GNNs?
So anonymity is maybe just something so in a way, if you think there's certain situations where you don't want anonymity, because anonymity kind of implies that in certain way you want to learn a model for a specific node. And this we will see again in the second half, in the third formally section of my talk, where I'll talk about knowledge graphs. And I think it's to a certain degree an open problem here. How do we apply graph neural networks to unseen nodes, to new nodes, to new subgraphs, rather than learning the model from scratch on a new data set, right? On a new, integrating this new part in a graph and retraining the model. And one way of doing this potentially would be defining features of the nodes, as we do in many other cases. But one of these implications of these theoretical results, and we actually lose from representation perspective. So it's kind of maybe important for certain features at least to have a unique identifiers of nodes and learn unique basically features for the corresponding nodes. Without doing that, you might pay certain price from model expressivity perspective. So I think it's not entry. This is some result people knew for a while. There is a lot of discussion about this, but direct practical implications is still something which is worth figuring out. But it seems like an important factor.
Okay. So another question from Ivan De Prado. So the graph, the edges is different for each input, but the weights are shared, right?
Yes. The weights are generally shared. So in all the graphs, in all the models you've seen so far, there is a complete sharing. There may be no sharing between layers depending on a specific model. So it's like in a normal transformer, in a popular these days transformer, right? You can have nodes, parameters specific to layers, or you can have something like a universal transformer where parameters are reused across layers, and these similar choices are made in a graph neural networks.
Okay. So Marco Gaido says, in the MT example, if I understand correctly, the CGN is put between the encoder and the decoder, so it is an additional network between them. If this is true, does the benchmark consider base models with the same number of parameters?
Yes. I haven't had time to really talk it, but if you look up in the paper, we modify the number of parameters, and instead, for example, feed-forward layers trying to control that, we are getting improved results, not just because the model is larger. That's a good question.
Okay, so the last question, Mohamed Amin Delabes asks, is the input data in the form of an adjacency matrix?
It depends what you like, what kind of tools you use. Whether your graph is sparse or not sparse. Also, this is something you can decide depending on application. For specific models, I don't remember. I'm sure we used adjacency matrices in many cases, but in certain cases, that was other ways of representing graphs was computationally more effective.
Okay, so some more questions popped up. So another question by Ivan De Prado: are nodes identified? Some kind of encoding is included in the feature vector?
In these cases you saw before, we basically haven't used any kind of identifiers, but in most of the cases we have encoder below, right? It will be like wireless TM transformer or something, and transformer in words themselves had, for example, position IDs, right? So this information gets propagated in a graph neural network. In the other part, in what's coming, you will see slightly different situation where you would have, for example, embedding individual, basically IDs for every node in the knowledge base. But maybe I'll better answer, if it will be unclear, it's better if I answer this after the second part of the talk.
Okay. And Daniel Varab asks, how sensitive are GNNs to connectivity, fully connected / sparsely connected?
I think there's some advantage of course, using sparsely connected graphs, especially with knowledge bases, because you can make this more efficient. There's some tricky from learnability. It seems a bit harder to train the model which have a very varying degree. So this is a practical problem in knowledge bases, because you might have nodes which have very many neighbors. So if nodes are entities, for example, United States will have many neighbors, and then you will have some other nodes which will have just a few neighbors. First of all, it seems to be a little tricky to learn in this setting. And then another issue is a capacity problem. So if you have the same bandwidth, basically the same width of the network for these different nodes, it might create a bottleneck. So there's still lots of open problems how to deal with this situation. In a situation you've seen so far with NLP non-knowledge bases, this seems to be less of a problem. With knowledge bases, this is, I think, one of the limitations, and this is also still an open question: how do you deal with this extremely varying degree of nodes? Okay.
Okay, a few more questions in the meantime. Joyon Zhang, each sentence have different syntactic structures. Therefore, in the generated syntactic graphs for the GNNs, they will need different weights, or how are they shared?
I'm not sure what shared. Yes, indeed, every sentence will have a different syntactic structure, mostly, right? And this is predicted by the parser. And we have parameters associated with edges, with edge types, right? With syntactic dependency relations. And these parameters will be shared across sentences, indeed. Yes, and also maybe should mention relation between these models and transformer models again, and this is something we can also discuss more formally towards the end of the talk. But why I want to mention it here, because there is, I think, also a pretty cool paper by Emma Strubel. So she positions this as a transformer, but basically one of the heads of the transformer is trained to predict the syntactic graph. So it's basically like a graph neural network. So first of all, it shows that you can integrate these two things more tightly rather than putting one on top of another. And then also from the computational perspective, it can be made much cheaper, because at test time, graph neural network is just one of the heads of the transformer. So there is still highly parallel architecture, right? So it can be done very efficiently within a normal computation of transformer.
Okay. There was a follow-up question by Marco Gaidu, another question on the MT example. Did you check what was improved in the translations? I mean, apart from blur, were there specific patterns in the produced translations that were improved over the baseline?
I think we should have been a bit more careful. I should admit that we tried doing some checks, but this was somewhat informal. So if you look into semantic, so we looked into length of sentences and length of dependencies, but also if you look in the semantic, we seem to notice a few examples where this had to do with certain type of So what is happening in English? You can say something. I taught class to students, or I taught students to class, and this is called alternation. And there's certain ones which are more typical than the other ones, but often they will have the same translation, for example, in the target language, or there's some kind of isomorphism to how you express this representation. And it seems to improve when we integrate semantic structure. So we see that realizations which, if you play this and rephrase following these alternations, models seem to be behaving more as you would expect. So it handles these situations better. But again, I don't have very formal, there is no formal benchmark with this. So it may be just we're lucky and selected, a couple dozen examples where it worked. It's a
okay.
bit hard to say.
Right. So we have one last question, so that we can proceed then to the second part by Juan Mancoria. Do we need to know the graph structure in advance, or can we let the network discover it? Will that be related to attention?
I think that is a very cool question, and it's a nice last question, because that's what will be answered also in the upcoming part of the talk.
All right. Thank you very much. Thanks.
Welcome back to the talk. I hope we've had a nice discussion about GNNs and GNN encoders. And now we look at slightly different application of GNNs and modeling of knowledge bases, and specifically the link prediction problem. Link prediction is a standard classic problem in this area. So you're given a knowledge base with some missing information, missing facts, and basically all the knowledge bases are like this, they're all incomplete, and you're asked to predict the missing information. Have to take a look at the example in the slide. So here we have a few facts about Mikhail Baryshnikov, a famous Russian-American ballet dancer, and these facts are represented as a knowledge base. And you asked if he lived in St. Petersburg or not. So let's take a quick look at this knowledge base and try to understand if he lived or not. it might be enough. So what you can see is that we don't really have an obvious proof, very strong evidence that he has lived. So we can't really conclude, but it's rather plausible. And so why is this plausible? First of all, because he studied at the Vaganova Academy, which is located in St. Petersburg. Also, he danced for Mariinsky Theater, which is also in St. Petersburg. And taking this information together, we are likely to conclude that, that he lived in St. Petersburg as well. This is our prediction as humans, but we want our statistical model to capture similar regularities. So we want them to detect passes, detect subgraphs which are predictive of certain type of inferences and make these predictions. So what are the classic approaches to, what are the standard approaches to link prediction? At least statistical approaches to link prediction. I would say this knowledge-based factorization. And in knowledge-based factorization, you associate node embeddings with entities, so embeddings with entities. And then you use these embeddings to score compatibility of entity pair and the relation. So you essentially score how plausible is a given triple, how plausible is a given edge in a knowledge graph. So this is a specific, rather simple factorization from about 10 years ago called Rascal. So here you take a product of these three terms, so it's bilinear form, and the lived in relation, and any relation is represented as a matrix. If you think this is a simple model, actually the state-of-the-art models for this task just a few years ago used diagonal matrices, and they achieved, and they're still not surpassed by much. So now we have a scoring function, and how do we, the question is how do we estimate parameters of the scoring function. I'm not going to go in details of loss functions, but intuitively what you want to score triplets in the knowledge base, so edges appearing in your training knowledge base higher than arbitrary random unobserved edges. And the loss function will encode this intuition. If you're familiar with how word embeddings are computed, so some of the standard techniques like skipgram, there are lots of similarity between these techniques. So you can guess how this loss looks like. What we do to apply graph neural networks to knowledge bases is conceptually very simple. So instead of using embeddings in the scoring function, we use representations of entities, representations of nodes computed by the graph neural network. So the scoring function stays the same, but instead of embeddings, we get node representations. So let's get a bit of intuition. So what is happening when you apply graph neural network to a knowledge graph? So as we know, after one step of message passing, nodes incorporate information about immediate neighbors. So in this case, the node for Vaganova Academy will include the information about St. Petersburg, and it will actually know that Vaganova Academy is located in St. Petersburg if the network is expressive enough. After the second update, this information travels further, so now Mikhail Baryshnikov knows its path to the St. Petersburg. So it knows that it studied in Vaganova Academy, which is located in St. Petersburg, again under assumption of sufficient expressivity. And then what do we do when we perform computation using the scoring function? Recall, we use representation of Mikhail Baryshnikov, we use representation of St. Petersburg after these multiple hops. And what you can think we are doing, we're basically measuring compatibility of embedding lifting with passes in the graph neural network. It's a little bit, of course, of a simplification, and this is not a single pass, but you can still think that this is capable, this model is capable of doing this. It can match the passes to potential relations between entities. And you don't need to explicitly enumerate all the passes. In principle, it can do it for you, because Node of Mikhail Baryshnikov now includes information not only about the path through the Vaganova Academy, but also information about the path through the Mariinsky Theta. Interestingly, this is only true with non-anonymous nodes, so it links to the more theoretical discussion in the very beginning of the talk. And this is the reason why we want to use not embeddings, but we still want to learn not embeddings rather than just using some kind of coarse entity types. This gives more power to our graph neural network. And this is power actually comes at a cost, because ideally we want to be able to apply models to new entities, to new subgraphs without having to retrain the model. But this is essentially an open problem, how we can do this with relational graph neural networks, how we can ensure that we can apply models to new entities. Of course, with learned embeddings, you can't really do this, because you need to estimate them somehow. Okay, so how does a graph neural network looks like? So there is nothing really new for you in this neural network. So it's very similar to the models which we used in the context of syntactic encoders. The important difference here is that you have many more relations. In realistic knowledge bases, rather than the benchmarks we use in academy, there are even more, there are many thousands of these relations. And so you don't want to have individual matrix for every relation. And so there need to be some parameter sharing. I'm not going to discuss what we used in this work, because recently there are better proposals, and also there are more interesting, more comparison, also more diverse sets of tasks. And I mentioned in the very beginning some references. Okay, so how do we train a graph neural network? So we already know how to train factorization models, but there are certain differences. And essentially, the way we train them can be regarded as a training denoising autoencoders. You might be familiar with denoising autoencoders in the computer vision context, or maybe unsupervised MT context. But the idea here is rather simple. So you take the entire training graph, but then you don't want to encode the entire graph. What you do, you produce a noisy version, in this case just dropping some edges, some subset of edges. And you encode this graph with a graph neural network. Then, using the nodes and the scoring function, you are now recovering not only dropped edges, but all the edges in the graph. So you formulate this ranking loss on edges, which is basically the same loss as was used for factorization models. I should also say that mention some limitations of using denoising autoencoders here, because this is the question how many edges you want to drop. If you drop too few edges, the model is likely to overfeed, because graph neural network is rather powerful, so you really need this certain amount of noise. If you start dropping too many edges, you're likely to disturb your passes, and at least you won't be able to capture long passes. You won't be able to, it doesn't make sense then to use a deep graph neural networks. So that's also a certain open problem. How do you train graph neural network effectively in this setting? So there may be better ways to train the model. Okay, so now I also want to make analogy with what we've done with in the part 2 when we considered GNN encoders of text. So there we basically plugged in our GNN layer in between standard encoder and the decoder. And this is essentially what's happening here as well. So in standard factorization, you can think that you have an input which is followed by scoring function from a factorization model, and then you have a loss function on top. When we apply graph neural networks, between input embeddings and the scoring function, we plug in a few layers of graph neural network. So the situation is rather similar. So how well all this works? I don't think it makes sense to look in the numbers too much here, because it's been a couple of years ago, situations has changed. But the crucial message I want to make here is that this model improves over using factorization directly. So it's useful to incorporate this computation of graph neural network. And also the error profile, if you read the paper, looks different. So it starts to model more complex relations. I also promised you in the beginning of the talk that I will link back this knowledge bases to modeling text, and we haven't really done this work in my group, or maybe we haven't quite succeeded in doing this. But the other groups did, and this is a picture from a work by Suna et al. From a CMU team. And so what they did, they considered question answering, and it's question answering using information in a knowledge base and in text, so in Wikipedia, in Freebase. And they link a knowledge base, they link Freebase to Wikipedia. So you have some entity linker used here, and so they have this rather large graph, and they perform apply graph neural networks to this graph, and then they can use this joint representation to perform question answering. Quite similar models have been also studied by Sorokin and Gurevich from Darmstadt University. So let me summarize this section. So we discuss how a link prediction task can be tackled with graph neural networks. And I would argue that GNNs are quite a natural tool, you may say an elegant tool for reasoning on top of knowledge bases and text. There's still many open problems. We discussed issues with applying models to new entities, with training. And we can't really say that this question answering on knowledge-based text is an entirely success story. This is still not default models used in a question answering. So they're interesting open problems to continue working on. So now let's discuss consider the final part of my talk, which I entitled Advanced Topics. But these are basically two somewhat unrelated topics. One deals with applying GNNs to induced graphs, or maybe I should say inducing graphs and applying GNNs at the same time. And another one deals with a serious shortcoming of GNNs and generally deep neural networks, that we can't really understand how the model arrived to these decisions. And we will try to tackle this issue. And this is really an ongoing work. But first, GNNs over induced graphs. In part 2, we discussed how we can incorporate linguistic structure predicted by parsers, by linguistic tools into narrow encoders. But this was kind of detailed linguistic knowledge, so it's given by the tool which was estimated on the annotated data annotated by linguists according to some theory. And this theory, these structures may not be compatible with what you need in downstream applications, maybe not optimal or maybe not even suitable for your downstream application. Also, the quality of these tools may also be a limiting factor. We've made a lot of progress with syntactic parsers, but this is again about syntactic parsers. This is mostly about English and a couple of other high-resource languages, and also about in-domain, so testing these parsers on essentially news data. If we go beyond this, linguistic tools are not necessarily that reliable and that robust. So what, instead of making these very strong assumptions using this very specific linguistic knowledge, using more general inductive bias? So, for example, for a certain problem, you can say that it's a good idea for us to model representation of text in a bottom-up way, in some structural way, and then trees maybe a natural inductive, provide a natural inductive bias for your model. So you can say, I want latent structure, and this latent structure should be trees. Or you might want to use some relation between mentioned in text, which you intuitively think should behave like a coreference, so they should connect mentions corresponding to the same entity, but you can't or don't want to use off-the-shelf coreference tool. And again, you can just characterize the topology of coreference graphs and constrain your structure to be like this. But the key point, you won't be defining the structure, you will be inducing a model to predict the structure within this given structural constraints. So it might be easier to understand what is happening if you look in the picture on the right. So what you have here is input text, input sentence, and from this input sentence X, you predict a structure. So I use a letter T because we'll be talking mostly about trees in a few subsequent slides. And then relying on this tree, you predict a label for the downstream application. So you have a supervision at Y, you have input X, and T is something what you're inducing. And basically you have two components here. One is a parser, a structural prediction model. So this is it predicting T from X. And then you also have a downstream model which relies on this structure. And I think, as you can guess, this component will be using graph neural networks. I think it's useful to think of this in probabilistic terms. So we are effectively sampling a tree from a parser, and then we're using this tree by another probabilistic model. And if we could, we would have just summed up, we enumerated all these trees and performed this summation marginalization over the structures. But this is intractable. And this is a problem, and this is especially a problem for us as we want to learn the parser parameters, so the parameters of the model PT given X, and it's hard to get a gradient estimate for this. So what does it mean hard, and what we can do? So in principle, formally these are discrete variables, stochastic variables, and they sit in our computation graph between our target variables and the input. So in principle, we can't really propagate our gradients, so you get some kind of block for your back propagation. So one option, and quite a viable option if you're careful, if you know what you're doing, is to use reinforcement learning, but still the problem is the variance of your gradient estimator can be quite high. So another option is to use sparse map. I'm a big fan of this class of techniques. So in this case, you encode preference for sparsity effectively of the structures. So only few structures have a non-zero probability, and if there are few structures, then you can perform exact summation, exact enumeration over these structures. Sparsity may be a good property, but also it's not always something you want. So it's certain inductive bias, and maybe also make learning sometimes harder. Another option is to use structured attention, but in this case, you're not really passing the structure. So what you're doing, you consider all the potential edges and compute the probability that it appears in the tree. So this will be edge marginals. And you passing this probability, so you're passing this weighted graph to the model which predicts Y. Another line of work which we consider it in our group is what we call perturbance parse, and here we can perform approximate sampling of trees of structures and use a differential dynamic programming. So we do pass, in this case, trees or approximation of trees, but gradients approximate, so that we get a biased estimates of the gradients, so there is a cost connected. So in a couple of the next slides, I will be looking into specifically in these perturbance parse techniques, but many things I'm gonna say will apply also to other options we consider here. So let's look in a specific application. So this would be natural language inference, and basically the same thing as a textual entailment. So in a natural language inference, you're given a premise and a hypothesis. So for example, you have a sentence, a man walking under umbrella, and this is a premise, and you have a hypothesis, a stranger carrying an umbrella, and you want to say if hypothesis is entailed by premise, if it contradicts the premise, or we don't know, so natural. So that's the task we want to consider. And there are a few different models we can use. We use a rather simple and elegant model, decomposable attention. So this was essentially a precursor to transformers. So it has a lot in common with transformer models, also from Google. And the key point here is that it kind of relies on attention between two sentences, between hypothesis and premise. So if you're not familiar with attention, attention is some way of encoding alignment between these words in two sentences in some soft way. Other details are perhaps irrelevant to our discussion. And so what we do here, we also incorporate layers of graph neural networks into the encoders. So now we're not just using embeddings and maybe position embeddings, but we also inform them by the latent structure, by the structure. But the key point, the structure is predicted within this layer. Right? So we have this differential dynamic programming, and we learn what kind of structures we want to predict, what kind of structures will help to improve performance on this task. So on this picture, it looks like if we only applied this machinery to the hypothesis, but the model essentially is symmetric, so we do the same for the premise. Again, absolute numbers may be not so important, so we look specifically in ablation tests, but there are a few things which I think are interesting here. So we compare here graph neural networks over these trees, so over constrained structural space, is not using any kind of constraints or not using any kind of dependencies in the input. So we can see that modeling these dependencies helps. But what is, I think, is more interesting and more aligned with the arguments I was making before is that we get improvements from using the constraints, from constraining our structures to be trees. So latent heads here is a model which is basically exactly the same. Everything is the same except for the lack of constraints. So it's not forced to be a tree. Every word selects its parent in the graph independently. So constraining structures appears to be beneficial. And what are these constraints? So I mentioned trees. These are not simply dependency trees like we saw before. These are projective dependency trees. And if you don't know what projective means, it essentially encodes as a tree captures hierarchical decomposition of the sentence. That's hierarchical, and I think it makes sense. Makes a lot of sense for SNLI, because what is crucial there, it's not some kind of expressive deep syntax, but it's still a good idea not to align individual words, but align some kind of phrases, some kind of spans. And this hierarchy trees basically model captures this hierarchy of spans, encourage you to represent these hierarchies, and this appears to be helpful. So this concludes this part about latent structures. So my take is that if you have linguistic tools and you think that they provide good biases, why not to try using them? But in many cases, you can get away by just making more general assumptions, and it can also help you. So some of this work at least started before transformers in the times of recursive neural networks, LSTMs, which didn't have explicit representation of the structure. Transformers are interesting beasts, and they're related to graph neural networks in many ways, and you can think that they're graph neural networks on a full graph, but also they at the same time use attention, so this means they induce the graph, right? So some kind of soft graph. Maybe it's not very comprehensible to me what I'm saying if you're not familiar with transformer. I'm sorry, we don't have really time to go over transformers. Hopefully it's covered somewhere else in the summer school. But what is interesting, these models, at least in certain settings, at least to a certain degree, also induce interpretable graphs. And this is essentially a net for our paper, and also Lena Voita's blog post, where she looked into individual components of these transformer models and saw that some of these components are interpretable and have an interesting and linguistic interpretable functions. Okay, now the final bit, extracting explanations. I would argue that extracting explanation from genomes is extremely important, especially considering what kind of applications we are looking into. So question answering, or multiple documents, or link prediction from huge knowledge bases. It's not enough just to make a prediction. It's really crucial to explain where this prediction comes from. So this is crucial for many reasons for question answering system, because of the trust, because of our models will still make mistakes. At least users need to be able to understand if the model potentially makes a mistake, and also maybe for legal reasons. And we don't have really much of machinery to do this. So this is in general new and a hot area in NLP, and there is very little work. There is only one single paper published on extracting explanation from genomes, at least as far as I know. So we want to understand which passes models rely on. So what kind of information flow you have inside graph neural network. So let's just recall notation. So we have nodes which are we denote with H. M are messages, so vectors sent between pairs of nodes, and we have aggregation functions. In the simplest case is summation followed by a ReLU. And this is applied to multiple layers. And again, a few different versions can be used, and there is a connection to the transformer. So now what we do here to understand the flow, we take the original model, we run this model over our graph. So we get all the messages, we get all the representations of nodes. And then what we do, we make a prediction which nodes can be dropped. And this is a prediction from this current layer of the graph neural networks, from the current hidden representation from the current message. And then if we drop this edge, we disregard it in a new computation. So in the bottom case, you run the same graph neural network, but over this sparsified graph, over this pruned graph. So when we want to interpret this, we essentially use the same model, right? We don't change the model. So the only thing we estimate is this red part, the function which makes a prediction which edges need to be dropped. And so how do we estimate it? We force, we want the sparsified, the pruned model to agree with the full model. So that's the way we train them. So we make them agree with each other. We define some form of divergence between their predictions, and we optimize to have a minimal divergence between the predictions by, or maybe I should say to prune as much and not have a high divergence. That's probably a better characterization of what we are trying to do. So when we apply these models to some of the models we discussed earlier in the talk, we can get graphs which are considerably more sparse. So we can see that not the entire graph, only some parts, often small parts of the graphs are used to make a decision. It's a little tricky for me to show you graphs for multi-hop question answering, but we can also see, when we apply it, we have some interesting finding. For example, we used coreference, and if you consider ablations, coreference appears not to be particularly useful. But from this analysis of information flow, we can actually see that the trained model does use coreference information in a certain way. Then some graphs which are maybe easier to understand for what's going on are syntactic graphs because they're just smaller. And so in this case, this is syntactic GCN, the one we discussed before, but we discussed it in the context of machine translation. Here, this is used in the context of some semantic task, basically some form of information extraction. So you want to discover the underlying predicate argument structure. And this is the all edges from the full syntactic tree which are kept. And you can see that only tiny subparts of syntactic tree are kept. And so you can see that these are mostly passes between the predicate and the arguments of this predicate. And it turns out that these parts are rather similar to what we have used as fishes in pre-narrow times. So this model actually relies on a rather similar set of fishes to what people can crafting these fishes created. So this concludes my talk. And so we talked about different applications of GNNs. We discussed positive results, but also quite a number of weaknesses. We also touched on interpretability. So I should say that we have lots of open problems in this area, despite many successes. And there are lots of opportunities to do interesting research. So now I'm happy to take questions from you.
All right, thanks Ivan for the great talk. There is one question posted right now by Philip Didrusin.
Yeah.
Certain linguistic categories, labels, and structures may be fully knowable. For example, in a simple intransitive sentence, you may well be able to identify the subject and the verb with 100% certainty by looking up words in a dictionary, if they are non-ambiguous. Is it possible to utilize information like this that comes for free?
Yes, I guess so. It's also a bit of a question what is complementary to what simple encoders are learning without having syntactic structure, right? So it might not be actually the case that for simple intransitive sentence you really need the syntactic structure, right? So it's maybe harder cases which are more informative, but some of the things may be easier to specify as well with heuristics and make the model to learn. And I think one example of this we saw in somewhere in the beginning of the talk. So in that case, we marked mentions, identical mentions in a text and linked them by edges, by certain edge type we called match, and this was useful. And other example not in our work, but in someone else's work where they considered question answering for knowledge bases. And in this case, they also relied on heuristics for the match of fields, names of fields in a table and text. And this for creating some edges in a knowledge graphs. And this was very easy to specify and actually extremely useful to use. And this, you can put inductive biases, for example, approximate match or something like this, which may be hard to learn in the embedding space, but easy to define in a string space.
All right. Are there any further questions? So there is one more by Daria. Could you please comment a little bit on the hyperbolic embeddings? I've come across an opinion that currently they are really harder to train, and although they are pretty effective at capturing hierarchical relations, the improvement they give isn't that much.
I'm not sure this is really the question I should be answering, because I know this work a bit, right? But I haven't used them and haven't used them as a part of any model. So it's maybe better to direct it to people working on this topic. Even so, yeah, I heard some rumors, but I heard also positive things about that.
All right. Any further questions? So I have one question about the part of the work where you mentioned inducing structure, inducing the graph structure from data. How often, do you observe that the kind of structure that you are inducing agrees with the linguistic structure that you are expecting when you are optimizing for a particular task? Do you think that, for example, with latent syntax or latent semantics, it really matters what is the downstream task that you are optimizing for, or do you think that if you want to learn something about syntactics or semantics, you need to consider multiple tasks at the same time?
Yes, I think this is a great question. Yeah, it usually depends a lot on the downstream task, and I haven't really showed the syntactic the structures induced, for example, in SNLI. And if I would have showed it, you will see that then very different from syntactic representations. I think on one side, maybe sharing across task can help a lot. Or if your goal is inducing syntactic structure, you can also try to think of the model in factorized or put together in such a way that you would induce structure which looks more like a syntactic structure. Because nowadays we also know of grammar induction work which relies only on a language modeling objective, but still induces something which is somewhat similar to linguistic syntax, right? So it's still often there are some inductive biases maybe hidden in these architectures, but still we can see that this is possible. But typically you need to make an extra effort. So if we talk about some other types of structures, we often see something resembling linguistic structure. One example is also coreference. So on one side, we saw coreference being induced, for example, within a transformer when you train document level machine translation systems, depending on the target language, if resolving coreference. So just to recall, coreference is basically linking mentions of the same entity. And specifically, what was happening there is linking pronouns to noun phrases they refer to. Was happening because it was useful. But again, it doesn't maybe match exactly specific linguistic theory. So it's something somewhat adapted to the task, right? So yeah, I guess it also depends what your goal is, right? So maybe in certain cases you don't care about that much, right?
Mm-hmm. All right. Okay, I think this is it. There are no more questions right now in the panel. Thanks again, Ivan. This was a great talk.
Thank you very much, everyone. Thank you for listening.
Bye. All right. Bye.
Bye-bye.